All right, so now in this episode, we are going to talk about how we formally define Pareto efficiency and how we find the set of all Pareto optimal or Pareto efficient allocations. All right, so let's start with the definition. So an allocation, I'm going to denote it by X1A, X2A. So this is basically the bundle consumer A is going to get, and this is the bundle consumer B is going to get. So I have two goods. So this allocation is called Pareto efficient if, remember, all definitions are if and only if statements, but we nevertheless leave it as if. So here it is Pareto efficient if there exists no other feasible allocation. And I denote this second allocation as X1 tilde A, X2 tilde A. This is what agent A gets, and this is what agent B gets. So obviously this should be different than this one, because if they're the same, that means the agents are going to get exactly the same utility. So if there exists if there exists no other feasible allocation, so it must be feasible, such that agent A's utility in the second allocation is greater than or equal to his utility or her utility in the first allocation. Same is true for agent B, and one of the inequalities must be strict. All right, so what does that mean? That means there exists no other feasible allocation where one agent is getting better off without making the other agent worse off. All right, so that's what Pareto efficiency is. I'm going to talk about how we can find a set of all Pareto efficient allocations. Is there an easier way? And yes, there is an easier way. However, for this, I need the preferences to be a nice behaving preferences, like the at least as good as sets are convex, and so the utility functions has nice and smooth indifference curves. Basically, the optimization problem has an interior solution like the Cobb-Douglas utility function, for example. So here, what I need is the Edgeworth box. All right, so given the pure exchange economy, the initial endowments, we already know how to draw the Edgeworth box. So we put agent A here and agent B here. So that's the 0 point for A and 0 point for B, remember. So all the allocations inside and within the boundaries, inside this box, including the boundaries, is feasible. Anything outside of this box is not feasible. So therefore, if there is a Pareto efficient allocation, we should be looking inside this box, again, including the boundaries. All right, so what I would like to do is, put some indifference curves for agent A and agent B. But before this, let's remember agent A. So the agent A, let's suppose, has a utility function u of A, and agent B has a utility function u of B. And again, remember, I suppose that both of them has these nice indifference curves. So this is one indifference curve for agent A. This is another indifference curve of agent A. And as we know, as we move away from the origin, it means higher indifference curves, higher utility levels. So this is for agent A, right? So if you drove the indifference, this is good 1 versus good 2. So if you drove the indifference curves for agent B, also we assume that she or he has also very nice smooth indifference curves. And once again, as we move in this direction, it means higher utilities. So what I would like to do, right? I mean, in this Edgeworth box, basically agent A has exactly this shape. So this is sort of a total number of good 1, right? So the length of this, and this is good 2. So the same thing for good 2. So it is basically the same environment. It's just here the agent B's 0 point is on this sort of corner. So basically that means I have to, when I want to draw the indifference curves, these are what indifference curve of agent A will look like, right? And for agent B, let me use a different color. Agent B's indifference curves will look like these, because again, agent B's 0 point is this corner. So agent B gets better off in this direction, and agent A gets better off in this direction. So you see, I mean, there is sort of a tension between A and B. Agent A would like to push the allocation as further away from the 0, 0, and agent B obviously would like to push the allocation away from his or her 0, 0 point. So therefore, there's a tension between these two agents normally. Well, question is, what is, or in this picture, where are the Pareto-optimal allocations? Can I say anything about their locations? Well, I kind of can. So let me simplify this picture. So ignore some of those curves and these arrows, because we already know in which direction we love to go. I mean, these agents want to go. So what I will do is the following. So let's pick this point, right? Is this point Pareto efficient? So this point, remember, tells us consumer A is going to consume this much good 1 and this much good 2, while the rest, the remaining, basically, I mean this part is x1b, and clearly this part is x2b, right? So here, the thing is this Pareto efficient? Well, question is there any other allocation, feasible allocation, where both agents are going to get happier? I mean, they don't have to be strictly happier. One agent can be strictly better off and the other agent can be indifferent. All right, so that means we have to look at the at least as good as set for each agent. So what is the at least as good as set for agent A? Well, remember the definition of at least as good as? If you don't, please go back to those videos. So all these allocations are at least as good as for agent A than this allocation, this red allocation. Okay? Well, what about for agent B? So this is agent A, remember? And this is for the blue color is for agent B. Well, for agent B, the at least as good as set is, well, obviously those indifference curves continue. All these allocations. Well, what does that mean? That means any point in this region, all right, is going to be better for agent B, better than this red allocation, but it's going to be worse than this allocation for agent A. Meaning, so if you move away from this allocation, so instead of this allocation, if you give those agents some allocation in this region, agent B will get strictly better off, but agent A will get strictly worse off. All right, so it's not an improvement. Okay? All right, so that means, I can't say at this point is Pareto efficient. Nevertheless, maybe there's an improvement because there are a bunch of other regions I need to check. If you, for example, select any point in this region, well, this time agent B is strictly worse off, agent A is strictly better off. Well, probably you got the idea. We should be looking at the region where we shaded both in black color and blue color, because that region includes all, allocations that are better for both agent A and B. So for example, if I pick a point here, all right, this point is better than this point for A, right? Because this point will be lying on an indifference curve that is higher than his initial indifference curve. So which means agent A is actually happier if he moves from this red point to this red point. Well, what about agent B? Well, the same thing. Agent B is going to get better off because this indifference curve is going to be above his initial indifference curve. So therefore, this allocation is an improvement in comparison to this allocation, meaning actually, it seems it is possible to make one agent better off without hurting the other agent or without making the other agent worse off. And therefore, this allocation cannot be Pareto optimal. All right? So, what are the lessons we should learn from this? Well, once you pick a point and draw the indifference curves of each agent, if we generate an I-like, remember, so we have this I-like region, shaded region, well, then that means improvement is possible, and hence Pareto efficient. So hence the allocation cannot be Pareto efficient. Good. Well, that point was kind of random, where we actually generated this I-like region. So here, what I would like to do, I just want to iterate. So once again, let's pick one arbitrary point. So here, draw the indifference curve for agent B. It's going to look something like this. And draw the indifference curve for agent A. Well, obviously, I don't know the exact shape, but it's going to look something like this. Oops, this is A. I'm sorry. So, do I have this I-like region? Oh, yes. So, any point in this region is actually improvement for both agent A and B in comparison to this red line. So, you know what? This is not Pareto efficient because we can find another point, let's say this one, which is an improvement for both A and B, meaning this is better than this red point for both. I mean, let's call this point 1 and allocation 1 and this allocation 2. Allocation 2 is better than allocation 1 for both agent A and B. Well, is point 2, the allocation 2, Pareto efficient? Well, draw the indifference curve for agent B that is passing through this point. Draw the indifference curve for agent A passing through this point. Do I have I-like region? Oh, yes, still. What does that mean? That means there is a point here, there are infinitely many, but I can just pick one point where, let's call it 3, the allocation 3 is better than 2, which was better than 1, but who cares about 1 anymore because it's not efficient. So we eliminate it. 2 was the next candidate, but 2 is also not efficient because I found another better point, an improvement for both agents. So 2 is also not efficient. Well, the question is 3 efficient? Well, let's forget all this for a moment. Let's suppose, I mean, I don't know if you can see the trend, but at some point it may be the case that agent B's indifference curve is something like this. And agent A's indifference curve is like this. Oh boy. Where they're tangent to each other at this point. All right, so they're tangent to each other. So what does that mean? Well, that means the following. If you calculate agent A's at least as good as set, meaning if you want or if you're looking for improvement for agent A, well, you have to select a bundle in this region. If you're looking for improvement for agent B, you should be selecting some bundle in this region. So what does that mean? That means we can't find I-like region where both agents can get actually better off. So that means, oh, by the way, I did not really put anything here because, you know, these are where both agent A and B get worse off. Same here. So meaning if you pick some point here or here, both agents are actually worse off. So it's definitely not an improvement. So that means if this is the case at that point, meaning if the agents' indifference curves are tangent to each other at some point, not crossing, but tangent. So here, remember, they're crossing each other. So here at point 1, they're crossing. At point 2, they're crossing. So if crossing, well, then we are definitely going to have an I-like sort of situation. But if they're tangent to each other, we can't find this region where improvement is possible. So therefore, this point is Pareto optimal. All right? Well, what is special about this point? Two indifference curves are tangent to each other. Well, remember the definition of marginal rate of substitution? It was the slope of an indifference curve. And if two curves are tangent to each other, that means the slope of the indifference curve, this black indifference curve, is equal to the slope of the blue indifference curve. So the tangency line that's passing through these points are actually having exactly the same slope. All right? So what does that mean? This is what it means. If allocation is Pareto optimal or Pareto efficient, all right? So sometimes I just cheat. Instead of writing Pareto efficiency in long, I just say PO, Pareto optimal, all right? It means the same thing. Pareto optimal or Pareto efficient means the same thing. So if an allocation is Pareto optimal, well then slope of the indifference curves of agent A and B must be the same, which mathematically implies marginal rate of substitution of agent A is equal to marginal rate of substitution of agent B. All right? So we know how to calculate marginal rate of substitution of agent A. We know how to calculate marginal rate of substitution of agent B when they're differentiable, obviously. And so, this equality basically going to give me all set of Pareto optimal allocations. Why do I say all? Well, because this tangency does not really have to occur only on one point, right? Actually, it would be an extremely rare situation where these two indifference curves are tangent to each other at just one point. Well, there are infinitely many points normally. So, for example, this is the indifference curve of agent A, and this is the blue color. This is the indifference curve of agent B, and again, they're tangent to each other, but totally different point. So, is this point Pareto optimal? Yes, it is. Why is that? Well, because if you want to improve one of the agents, that means if you want to improve agent A, you have to move in this direction. I'm sorry, I should have used the black color, but that's going to hurt the player B or the agent B. If you want to improve agent B, you have to move in this direction, but that is going to hurt agent A. So therefore, it is impossible to make one person better off without hurting the other person. And so this one is also efficient. But you said this is also efficient. Well, yes, it is. Remember the splitting $100 example? There were infinitely many Pareto optimal allocations. Here, same. There are infinitely many Pareto optimal allocations. And in fact, normally, there's going to be some curve connecting this point to this point where at all the points on this curve, the indifference curve of agent A and B are actually going to be tangent to each other. So normally there are infinitely many Pareto optimal or Pareto efficient allocations. And by the way, this curve we call contract curve, or the set of Pareto optimal or efficient, same thing, allocations. So let me underline few very important things. One, well, this point is Pareto optimal. What is this point? It is the point where agent A gets 0 of good 1, 0 of good 2, which means agent B gets everything. So this is more like agent B gets entire $100 and agent A gets $0. So it's very similar and it's efficient. All right, so symmetrically, this point is also efficient, meaning agent A gets everything and agent B gets nothing. So that's also efficient. And any point on this curve is going to be efficient simply because the margin rate of substitutions of agent A and B are equal. However, the second important remark that I want to make, well, this statement is true if and only if the utility functions UA and UB, as I said, have nice convex, at least as good as sets, or sort of if they have interior optimal utility maximization solution. So if they are, for example, a straight lines like perfect, so if good 1 and good 2 are perfect substitute or perfect complements for these agents, obviously tangency is going to be impossible. All right, so how can we solve those questions? Well, it's going to be a bit challenging, bad news, because I can't really use this equality. You have to draw the Edgeworth box and figure out where the optimal allocations will be. Like the very first example we did with the utility functions 2x1 plus x2 and x1 plus 3x2, if you remember the story of Anita and Bob. So you have to draw the indifference curves and figure out where the optimal Pareto efficient allocations will be. So when this is possible, well, when, for example, the utility function of these agents are something like minimum of ax ax1 bx2, for example, or something like utility is equal to ax1 plus bx2, meaning the marginal rate of substitution is not well defined, or the marginal rate of substitution is always a fixed number. And obviously, if the agent A's and B's indifference curves are not tangent to each other, that means their indifference curves will never be tangent to one another. And so, therefore, this condition is not going to give me the Pareto optimal allocations. So once again, in those instances, I have to draw the Edgeworth box indifference curves and then figure out where the optimal solutions will be. Hopefully, I am going to solve an example for this specific case. But otherwise, we can always use this equality to find Pareto efficient allocations. An example is coming up.